This is Unit 11, Organic Chem, Lecture B. We're talking about hydrocarbons today. Hydrocarbons, remember, are made of hydrogen and carbon, and that's it. Hydrocarbon, that's all that's in there. If there's anything other than hydrogen and carbon, you're going to use reference table R. There are many different homologous series of hydrocarbons. Homologous meaning that they have something in common or the same. So these guys have similar structures. They're all going to use the same general formula. The only three series of hydrocarbons we're responsible for are alkanes, all single bonds between carbon. Alkenes have one double bond, and alkynes have one triple bond between two of the carbons. When you have the one double bond, it does not have to be on the first carbon. It can be on a different carbon within the molecule, but there's only one of them. Same goes for the triple bonds. When we look at different structures for any of the homologous series, and we put the correct number of hydrogens on these guys, they are going to be different always by one more carbon and two more hydrogens. So if you have 1, 2, 3, 4, 5 carbons and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, this one that has 4, 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Always different by one carbon and two hydrogens. The homologous series endings of their names are going to be the ANE, ENE, YNE from alkane, alkene, alkyne. The beginning parts of their names use the prefixes from reference table P. Remember, this is how we count to 10. Metheth, propu, penthex, heptach, non-dec. Whenever you see one of these word roots in a name for an organic molecule, it is referring to a number of carbons. General formulas on reference table Q are used to help you identify which of the homologous series you have. So if I have something like this, C2H4 and C21H42, and they want to know which series it is, which general formula works for it, you have three choices for your general formulas: CnH2n plus 2, CnH2n, and CnH2n minus 2. The N refers to the number of carbons. So I take the two carbons and plug them into the formulas. If I look at the three general formulas and I plug 2 in for the N, if it were an alkane, then the 2 would give me C2H6. If it were an alkene, it would be C2, 2 times 2 is 4. And if it were an alkyne, it's Cn, so C2, and 2n minus 2, so 4 minus 2 is 2. You can double check it by using the other one, plugging 21 in, so the only one that matches is this. They don't want to know, though, in this question whether it's an alkane, alkene, and alkyne. They want the general formula. The general formula would be CnH2n. Sometimes they will ask you to identify the homologous series, and that's going to be one of those three. So if we look at the other example, we have C6H10, so you either have 2n plus 2, 2n, or 2n minus 2, so you plug the 6 in. So you have either 12 plus 2, or 12, or 12 minus 2. And it's going to be the 12 minus 2, so the general formula, CnH2n minus 2. You can double check by trying it with the 10. 10 times 2 is 20, minus 2 is 18. The three types of hydrocarbons that we need to look at: alkanes, alkenes, alkynes, all listed on reference table Q. You're going to look at the ending of the series to figure out which type it is. So alkanes all end in ANE. They have only single bonds between the carbons. Because they're all single bonds between the carbons, if we want to add something to it or change it, we're going to have to remove a hydrogen. So these guys are our saturated hydrocarbons. The beginning of the names are going to tell you the number of carbons, and the ending of the name, ANE, tells you the type of bond. So I'm going to write down some examples, and we'll take a look at these. When you go to find the molecular formula, you should go to Table Q and find the general formula. For alkanes, it's CnH2n plus 2. Then you look at the names and check out the prefixes. The prefixes you look up on Table P. Meth means 1 carbon, prop means 3 carbons, and hex means 6 carbons. So if I were to take that 1 and plug it into the end, I have C1H. 2 times 1 is 2, plus 2 is 4. We'll do the same thing for propane and hexane. When we draw their structures, start with your carbons. So methane has 1 carbon. Put the hydrogens around, 1, 2, 3, 4. You can write the hydrogens in as little h's. Or, when we do propane here, I'm going to do it a simplified way. 1, 2, 3 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. You can just draw the lines without writing the h's. Both are acceptable for our final. Draw straight chains and make your life easy. So let's look at what hexane would look like, straight chain. Again, when you're all done, straight chain, check to make sure that your carbons have 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, etc., etc. Count your total number of carbons, count your total number of hydrogens. They should match your formula. Next series are the alkenes. The name alkene ending in ene, we can find that on Table Q, has the general formula CnH2n, and if you look at their example, what's important about that is that there is 1 double bond between 2 of the carbons. This is going to make it in the unsaturated category. We can just break that double bond in order to add more hydrogens. We don't have to remove anything. The ending of the names end with ene. The prefixes, again, are going to be your numbers of carbon. So let's write down the name of a few examples. You have the general formula, you have the names. Eth means 2 carbons, but means 4 carbons, hept means 7 carbons. Again, we got those from Table P. Plug the 2 into the formula, C2H4. We'll do butene and heptene. Note that ethene is going to be your smallest alkene because you have to have the double bond in there, which means you need at least 2 carbons. So if we draw our structures out, you should draw the number of carbons first, put the double bond in, put it on carbon 1 to make drawing your structures as easy as possible, and then add your hydrogen so that each carbon has 4 bonds. You will see me draw the hydrogens on to these carbons on this angle. That's the proper way to draw them. The state will also take from you, because we don't have to do stereochemistry and know the angles, something that looks like this that is also acceptable. I'll draw the other 2 and we can compare their structural models. When you're done drawing structures, check to make sure you have the right number of carbons. Each carbon has 4 bonds and you have the right number of hydrogens. Be very careful when we're doing alkanes and alkenes right here where that double bond is. That carbon only gets 1 hydrogen. It doesn't matter whether you draw the 1 hydrogen off the top or off of the bottom, because mirror images are going to be the same thing. But don't put an extra hydrogen down here at the bottom. That's a common mistake. That would be wrong, because that would give this carbon 5 bonds instead of 4. So just watch out for that error. Other than that, pretty straightforward. Last hydrocarbon from Table Q are the alkynes. The YNE ending tells you it's an alkyne. Of course, it's going to be unsaturated because you can break this triple bond. It has 1 triple bond in it. The first member, called ethyne, has 2 carbons because eth means 2 carbons. It also has the common name acetylene. So acetylene torches have ethyne in them. Ethyne would be its IUPAC name. General formula for the alkynes, CnH2n minus 2. We're going to draw just a couple of these. If I have 2 carbons for ethyne, that's going to be C2. 2 times 2 is 4 minus 2 is 2. Structural formula your 2 carbons with 1 triple bond. Each carbon already has 3 bonds, so they only get 1 hydrogen each. Propyne, prop means 3 carbons, so C3H. 2 times 3 is 6, minus 2 is 4. 1, 2, 3 carbons. Again, put the triple bond on carbon number 1 to make things easy. This first carbon needs 1 more bond to give him a total of 4. This middle carbon already has 1, 2, 3, 4 bonds, so he doesn't need any hydrogens. And the last carbon needs 3. Again, the most common mistake is to put too many bonds on this middle carbon because he doesn't have any hydrogen. So there's a nice easy pattern to the hydrocarbons. Use table Q. When we have carbon rings, if they have all single bonds, they're cyclic. We'll call them cyclopentane, cyclohexane. But there's a special series called the benzene series that we're just going to touch on briefly. They're important because they're called aromatics. They're going to make all kinds of artificial scents, artificial flavors. Benzene itself, the very first one in this series, is deadly poisonous, and it's a special kind of ring because it has alternating double and single bonds. So I'm going to draw you a couple of structural formulas for it. Recognize that this is benzene. C6H6 is its molecular formula, and just pick it out. So I'm going to draw you a few structural formulas. So you can draw it as this hexagon with every other bond between the carbons being a double bond or a single bond. There are simplified versions of this, and they would look like this. In the simplified version, every corner represents a carbon. The double bonds are shown to you in this first version. You're supposed to know that there's hydrogen sticking off of each corner. In the other one, the circle is there because these bonds don't stay in place. Because these molecules move and they flex, the bonds flex back and forth, and so that's what the circle is representing. Again, you're supposed to know each corner is a carbon and there's a hydrogen off of each side. The next one is bigger by 1 carbon and 2 hydrogens, and it's called toluene, also poisonous, and it looks like this. So basically this is a benzene that has a methyl group attached to it, meth meaning 1 carbon, the YL meaning that it's a branch. If you're looking up any organic structures, these types of models are going to become very familiar to you. For our purposes, you just have to recognize that they belong to this benzene series. And that's going to be it for hydrocarbons.